Okay, so the next thing we need to do with energy is talk about the extend it to multiple dimensions. So in this case, what we have is a force acting on this body that is not in the same direction as the displacement. So that, of course, requires multiple dimensions for us to think about. So what I would like you to imagine is that we've got a box sitting on the ground, and the box has a certain mass, and so it has a certain weight pulling down on it, and there's a force of gravity pulling down on the box. But the box is not falling through the ground, so there's some force that is pushing and holding the box up, so it's not accelerating down. And that's called the normal force, and it's perpendicular to the surface, so the box is sitting on this. This normal force is what you feel on your feet when you're standing up. You stand up for an hour straight, and your feet start hurting. It's because the ground is exerting a normal force on your feet, and that's the force that you feel. And then we're going to take it and we're going to exert a force sort of downward. So we're not pushing directly this way, we're pushing downward and everyone knows that this is an inefficient way to do things because you're exerting forces that not all of the force is being used to push this way. Some of the force is being used to push the box down. And we're going to see how that gets caught up in the equations that we're going to derive for work for this particular kind of thing. We're still working with a constant force, and we will work with a varying force in the next video. So for right now, we're dealing with a constant force, but we're having to do it with the forces of vector because we're dealing with more than one dimension. So we have a displacement here. We're calling that displacement delta x. We take the vector associated with position x2 minus the vector associated with position x1. This is again exactly the distance that the force is actually acting. So you're pushing down this way and this box slides, and then you stop pushing and you want to see what happens to it. Okay, for this particular example, we're working with a frictionless surface, but we can imagine adding friction in pretty easily here, and we'll talk about that a little bit later. So the question is, how much of the force actually acts to push the box this way? Because some of it's going to be pushing down and some of it's going to be pushing this way. So the way that we do this is first we establish a coordinate system. So and we would say that we generate a chart, and the chart is going to tell us sort of our coordinates in this particular example as we're going to analyze it. And so we have pointed up is the y-axis and pointed to the right here is the x-axis. Okay, so the displacement is entirely in the direction of the x-axis. That is, if we want to take this displacement vector and we want to assign it components, its components are going to be delta x and the x for the x component and 0 for the y component. That is, that remember, components are just a way of representing a vector, and these components say you move the amount delta x in this direction, and you don't move any up and down. And so this displacement vector moving this direction is well represented by these two components. Finding the components for the force is a different matter. So let's look and see what the components of the force are. So if the force is pointed down this way, we have one component that's the y component, the f sub y, and we have one component that's the f sub x. So the f sub x is the force acting in this direction, and then the f sub y is the part of the force that's acting up and down. And there's an angle here associated with the angle that the force is being acted on down to this position. So we can again represent this force by its x and y components, and a little trigonometry will show you that again the sine of theta is going to be the opposite over the length of the hypotenuse. So the length of the hypotenuse, the magnitude of the hypotenuse, we typically show with either putting these double bars on either side or just writing the letter itself. So we could also here write just f sine theta, and that's what I'll usually do, but here I want to really emphasize that we're talking about the length of the vector, not the direction of it. So the length of the vector times sine theta, and here this would be the length of the vector times cosine theta, gives you the x component. So we could write this is equal to the x component is f cosine theta, and the y component is f sine theta, where again the f here is the magnitude of the force. This is the number that you're used to associating with force. This would be a certain number of newtons, and that's the total amount of the force that we're actually exerting. Cosine of theta deals with the direction of the force that we're exerting. Okay, so what that's going to do is it's going to break things down into a portion of the force that's moving in the x-axis and a portion of the force that's moving in the y-axis. So we can redraw this, what's called a free body diagram. So a free body diagram is we imagine this whole mass as just a point, and we write down all the forces acting on it. So the forces acting on it are the weight pulling it down, the normal force keeping it from falling through the floor, that's acting up on it, and then the force that we're applying is acting in this direction. Now we can exchange this force for the two component vectors. And so what we would say is we could redraw this, and we could say that there's a mass associated with this. We have a normal force pointed up. It's the same as what it was before. We have a weight pointed down, which is minus mg. G is just the gravitational acceleration in a uniform gravitational field. It's about 10 meters per second squared, about 32 feet per second squared in U.S. customary units. And then this F, we're going to break down into two parts. There's part of it that's pointed in the x direction, so that's sort of like this, and that we're going to call F sub x. And then we have another part that's pointed straight down, which we would call F sub y, and those are magnitudes of these forces. And so what's interesting is in the direction that the box is actually moving as we're applying this force, the only part of the force that's acting here is the x component. So that's the only part that's actually pushing the box this way. Everything else is straight up and straight down. And so there's nothing else pushing the box except for the x component of this force. So let's define the work then. We're going to define the work as being the x component of this force times the magnitude of the displacement. So we're not looking at the, again, we're not looking at the actual vector of displacement here. We're looking at the length of the displacement, this distance from this point to this point. So that's the magnitude of the displacement, which again we would draw, but instead of doing these bars, we just do it without putting the vector sign up. So that would be just times delta x. Notice this equation looks exactly like the equation that we had. I think I've still got it here. Here, F constant times delta x. It's the exact same thing. It's F of sub x, but this is constant because this is a constant force times delta x. So this is exactly the same definition that we had before for work. And we're just sort of trying to figure out a way to get rid of the portion of the force that's not pointed along the direction of displacement. But we have an equation for S of x, and so what that is that this is going to be equal to the magnitude of the force times delta x. Well, delta x is just the magnitude of the displacement vector. So we can say times the magnitude of the displacement vector. And I'm doing this to be very pedantic here, very carefully saying that this is the magnitude of the force, this is the magnitude of x, and then we're going to multiply that by cosine of the angle that the force is being applied at. So this is this angle here, okay? This thing, go back and look at the videos that we did earlier on talking about the algebra of vectors. This thing is what we call the dot product, or it's sometimes also called the scalar product. And so what this is W is going to be equal to F dotted with the displacement vector delta x. So what we've discovered is a way of thinking about work in terms of dot products in vectors as opposed to in terms of magnitudes in scalars. And this is a more general expression than this one is. This one is a one-dimensional expression. It's the force acting in one dimension in the same direction as the displacement happens. This is a general force vector. It could be happening in any direction. And this is a general displacement vector, and it could be happening in any direction. So we can now define, using the same definition that we started with, which is a constant force times a displacement in one dimension, we have discovered the equation that will allow us to do the same calculation, but now using vectors in multiple dimensions. And we've only done it in 2 dimensions here, but this is extendable to 3 dimensions and 4 dimensions and 10 dimensions and 1 million dimensions. Whatever number of dimensions you want to work with, this equation will work, and we can, no pun intended, this is the equation for work, and it's going to be equal to the force vector dotted with the displacement vector.